Hi, I'm going to talk about online matrix factorization with convexity constraints and representative regions. This is a joint work with my co-authors Jin Hao Peng and Professor Olgita Milinkovic. Let me start by motivating the problem with learning problems on large datasets. In large image datasets, one of the important learning problem is classification. We want to classify image datasets into representative categories, and we want to identify representative samples for those categories. Similarly, in large genomic datasets, where each data point represents the gene expression data for a single cell, we want to classify the cells into clusters and identify representative cells, cell types for those clusters. Uh, in all of these large data sets, the dimension of the data is huge. So before doing any post-processing like classification or other processing technique, learning problems, applying learning problems, we want to reduce the dimension of these data sets to be able to post-process them easier. So the first step in these last data sets is dimensionality reduction. Um, our focus on this in this work is on this first step of dimensionality reduction. So for large data sets, we want to represent each data point as a convex combination, as a combination of a small number of basis vectors. And we also want these basis vectors to be interpretable in terms of categories of the data. Uh, let's look at existing approaches for dimensionality reduction in large datasets. A few of the existing techniques are feature selection, linear dimensionality reduction techniques like principal component analysis, uh, list analysis, random subset projections, and neural network techniques like autoencoders. A recent technique called non-negative matrix factorization has been widely used for large datasets because of its advantages over other techniques in terms of interpretability. So, first, let me briefly talk about what matrix factorization is, if you haven't heard about it. So, if you suppose that you have a data matrix X, which consists of n data points in an m-dimensional space, you want to represent the data matrix as a, a combination of as a product of the basis vectors k basis vectors d and their coefficient vectors. So each column of the coefficient vector matrix lambda corresponds to a data point, and it is represented as a convex combination of uh, k basis vectors. So why do we want to use a non-negative matrix factorization as over the other dimensionality reduction techniques? Non-negative matrix factorization provides a few advantages in terms over other existing techniques because it has lesser restrictions on the choice of the basis. And according to applications that we are applying to, we can add specific constraints on the basis to make them more interpretable. Constraints such as non-negativity, sparsity, and convexity. And uh, although neural networks are much more flexible, they have high computational costs, and they are very difficult to analyze um, compared to non-negative matrix factorization. So in this work, we focus on non-negative matrix factorization and algorithms for the constrained version of this problem. So let me quickly introduce the constrained matrix factorization problems, the non-negative sparsity and convex problems that I just specified. For non-negative matrix factorization, we want to first approximate the data matrix with its factor form d times lambda, while adding the constraints of non-negativity on the basis vectors and the coefficient vectors. This non-negativity constraints allows the basis vectors to be interpreted as components. So, for example, in topic modeling, each basis vector corresponds to a topic, and if a data document is represented as a non-negative combination of these bases, then we can interpret that document as containing components of those topics in itself. Sparse matrix factorization, on the other hand, tries to minimize the sparsity of the coefficient vectors, and it's more interpretable. Uh, this representation provides a more interpretable and accurate representation, and it's makes the and since sparse vectors are easier to store, it also provides advantages in that regard. Convex matrix factorization, on the other hand, constrains the basis vectors to lie in the convex hull of all the data points, and it provides interpretability for the basis vectors in terms of the data. Now, how there are existing techniques for matrix factorization. Uh, let's look at those existing techniques. So we want to solve this, minimize this approximation error when we want to find factors for the data matrix X. But this problem is non-convex and it's known to be NP-hard. Although there exist uh, algorithms that solve this problem in a sub-optimal manner, uh, many of these approaches follow an alternating minimization approach where iteratively we fix either the basis vector d, vectors d, or the coefficient vectors lambda and optimize over the other parameter. Uh, so in each step, we solve a convex problem and iteratively optimize until we converge to a solution. And it has been shown that using this methods, we can converge to a local optima. So this approach has its own challenges. There are a few challenges to solve this problem, though. So because matrix factorization techniques are computationally expensive and their computational cost increases with the size of the data set. So because in each for each data set we are solving a problem of k times n dimension and k cross n dimensions. So, but there exists an online algorithm that solves these problems uh, in an efficient manner. So, for non-negative and sparse matrix factorization, an online algorithm is known that sequentially processes these data and solves small con- uh, constant-sized convex problems in each step. But for convex matrix factorization, no online algorithm is known. And it's difficult to apply this technique by Myral et al. To this approach because the space is not known in the start. Our results focus on the convex matrix factorization problem, and we show that This problem can be solved in an online manner, and we provide guarantees for almost sure convergence for our online algorithm. So to present our algorithm, let me start with the existing online uh, matrix factorization algorithm by Myral et al. So we want to solve. Uh, so first, let us formulate the original matrix factorization optimization problem into a different form. Uh, Suppose that the data points in the uh, data set come from a probability distribution. Then we can write this minimization in terms of an expected minimization function. And although this problem is still non-convex and p-hard, it becomes easier to solve and easier to prove a guarantee them. So for this expected version of the problem, let me present the algorithm by Myral et al. So note that in this expression, the uh, the quantity capital X represents a random vector, and bold capital X represented the data matrix, and alpha is the representation of the vector small x in terms of the basis vector D. So the algorithm iteratively processes each data point in the dataset, and for each data point, given the previous estimate of the basis dt minus 1, it computes the coefficient vectors for that data point alpha t by minimizing the loss for that representation, and then updates the basis vector by fixing all the representations for all the previous points. Now note that in each iteration in this algorithm, we only need to solve small dimensional convex problem, and we do not need any storage because of this representation of these problems. So this algorithm minimizes this loss function g of d, uh, but note that we can write the empirical estimate of this expected loss function as this function g of t of d, gt of d. But in step 3, instead of optimizing this function gt of d, we are optimizing a different function where the alphas computed with respect to some other uh, previous approximation of the basis vector d. So we are optimizing a surrogate loss function in each step that is different from the empirical estimate of the loss function that we wanted to optimize, but this algorithm still converges to an optima of the original loss function g. So can we apply this approach to the convex matrix factorization problem as well? Unfortunately, it is impossible to apply directly this online method as we do not know from the start the space that the data points belong to. So we have to estimate the space as we go along and try to constrain the basis in that space, which it's not clear how to do. There are a few existing approaches that try to solve this problem. Let me describe one of them. So in archetypal analysis, the problem that the authors want to solve is represent the data point in terms of the extremal uh, data points of the data set. And uh, this approach uh, is a bit different from our approach where we want to only represent the basis vectors. Only constraint on them is to be inside the convex hull of the dataset, not the extremal points of the dataset. So in this way, we can these basis vectors can be the can be representative of the categories of the dataset. So let me introduce our proposed algorithm. So we want to solve the minimize the expected loss function for the probability distribution with respect to the probability random variable x, and constrain the basis d to be in the convex hull of to be inside the convex compact space corresponding to the support space of the random variable x. So let me introduce a bit more notation. So you want to optimize this problem. We can also write this function L by overloading a little bit and making the dependency on the coefficient vector a little more apparent. So our algorithm is similar to the online algorithm by Myra Latar, but there are a few major differences. We maintain an estimate of the space of the random variable x for each basis vector dt of I. We maintain an estimate x hat t of I for at each iteration for the compact space C, and sequentially we optimize update this estimate x hat and the basis vectors d for each data point as it comes in. So for each data point x, we update its coefficient vector alpha t by fixing the dictionary to the previous estimate of the dictionary. So for each data point x, we update the coefficient vector for the data point by minimizing the loss function for the data point and fixing the basis vectors to the previous estimate. Assign the basis vector to a basis element, to assign the data point to a basis element, and then update both the basis vector and the estimate of its bounding region for the compact space of C. So in a bit more detail for data point x, we compute its coefficient vector with respect to the previous basis vectors. We uniformly randomly classify the data point to the basis uh, element dt of I, and we find possible values for the estimate x hat t of I for this estimate of the compact space C. And for all of the among all of these estimates, we choose the best estimate that minimizes the surrogate loss function. And um, so this algorithm solves this expected minimization problem, and it also provides guarantees of convergence to a local optima of this problem. We also propose another alternate version of the algorithm where we solve this minimization problem, where instead of constraining the basis vectors to a single compact space, we want to constrain them to be in the uh, correspond to the clusters of the data set. This algorithm also comes with theoretical guarantees, but only if there is an intermediate classification step that is assumed to be correct. But it has the advantage of being able to use partially labeled data. So the proposed alternate version of the algorithm just modifies the classification step, where instead of uniformly randomly assigning the data point, it uses a heuristic approach to assign the data point to the basis elements, which correspond to clusters. And this approach now solves these two versions of the minimization problem. Our convergence guarantees are based on a few minor assumptions. Um, we assume that the data is approximately uniform in the compact space C, and that the error functions are well behaved, that is convex and bounded for these data points. Uh, Let me skip over the proof for our algorithm to go to the results. Uh, so here we show the performance of our online convex metric factorization algorithm. It's seen that it performs as well as the convex matrix factorization approach, but um, it works in an online manner and takes less computational power. And here is the amount of time it takes for the convex matrix factorization algorithm versus the other online algorithms. And here we show that they both converge to the um, same approximation error. So instead of synthetic data sets, here we show the same thing for single cell RNA data. On MNIST dataset of handwritten images, we show that this convex matrix factorization approach indeed produces um, more interpretable basis. And here are the results for uh, accuracy and of the running time of our algorithm on various other data sets. And we show that we can see that on larger data sets, our algorithm has higher, more advantages in terms of running time over other algorithms, and provides this similar performance guarantees. Thank you.